Hi everyone. Today what we're going to look at is kind of going backwards from where we've been. So we've been spending the last bit going through and being able to graph trigonometric functions. Today what I want to do is I want to look at being given the graph of a trig function, can we go back and create the equation that would produce it? So what you see on the screen right now, there is a graph of a trig function. And you notice the instruction would like you to go through and create both a sine and a cosine equation for each function. So you'll also notice then on the graph, we have some key values that are labeled. We have the y-intercept labeled, as well as the coordinates of a maximum and a minimum. So all I'm going to do at the very beginning of this is just list out some key properties of that function. So perhaps the first thing we look at is we could recognize that I have an amplitude on that function. I go all the way from 3 down to -1. That's going to tell me then that the height of this graph is 4 units high. And if my height is 4 units high, then I have an amplitude of 2. Well, the next thing that I'm going to look at is my period. Now, I can kind of eyeball this a little bit, but there's a better way. I could say, well, I know that my graph has this value of 1 at the very beginning. My graph then rises to a max, falls to a min, and returns back to a value of 1 here. And therefore, you can find that your period is 360 degrees. However, I'd like us to go through finding our period in a slightly different way. This way is going to be a little bit more than trusting our eyes. And for us, what we can do is we can examine then distance from the max to the minimum. We should be good that on any one of these periodic functions, my distance from my maximum to my minimum must always be half the period. Because to complete the full cycle of that graph, I would then have to return back to its max. And so if I was to look on that graph right now, I can see that I'm going from 90 up to 270, and therefore that distance is 180 degrees. And so if 180 degrees is half the period, then my full period must be 360. So using the distance from the max to the min to find your period might be really useful. And now with these two properties, you'll notice there are infinitely many trig curves that have an amplitude of 2. That is, there are infinitely many trig curves that have a height of 4. They could exist anywhere vertically. There are also infinitely many trig curves that exist that have a period of 360 degrees. But if we were to look at two other features, those will be able to nail down to the one specific trig curve that we see in front of us. The next thing that I think you would want to look for is going to be, well, where is the middle of your graph? So if we were to take a look at this curve and we notice that our amplitude is 2, then if we were to come down 2 from the top of our curve or up 2 from the bottom of our curve, then we have to arrive at the middle of our curve. And if I go down 2 from 3, I get to a value of 1, or if I go up 2 from -1, I get to a value of 1. That tells me that the middle of my graph is at a y value of 1. Therefore, the equation of the sinusoidal axis has the equation y equals 1. That tells us where our graph now must lie vertically. The next thing for us to deal with is to deal with where does our graph lie horizontally, and this one's going to get a little more difficult, or at least have more to consider. Let's go back to what the instruction said. And that instruction says that we need to go through and write a sine and cosine curve for each one of those functions. Now, the important part for us is that when we go through to write down our sine or cosine graph, we could have a very ugly function. And what I've done is I've listed how ugly that function could be. I want us to notice, though, that the maximum, minimum, and zeros or middle values of any sine or cos curve are going to change as you change from sine to cos. And so we really can't talk about this curve and how it exists or where it exists horizontally until we choose a sine or a cos function to talk about. The three features that we've already found, those never change regardless of whether you're talking about a sine or a cos curve. So let's take a look at the graph that we have right now, and let's try to pick which one would be the easiest function to build. I hope that what we can focus in on is the beginning of the function. That because we see that the middle of our graph is at 1, and since our y value is at 1, y-intercept, then we know that we're in the middle of our graph at the very beginning, and we rise. And we should be good that the middle of the graph and rising is the way our sine curve naturally begins. And so, if I had to choose which equation I was going to build, then I would build a sine graph. And so, for us to go through, then all we need to do is to be able to fill in all the components of that equation. And so what I mean by that when I say that is we need to fill in an a value, a k value, a c value, and a d value. Okay, given what we know about how to graph the functions, we should be able to plug in some of those key features right now. Right now in that equation, we should be good to say that we know that we have an amplitude of 2. Not sure on the k value yet, but I am sure on the c value. Because my graph starts in the middle and rises, just like my normal sine curve, that means there is no phase shift on this graph, and therefore my c value is 0. So I'm going to keep that x in there, but I'm just going to have a little placeholder for my k value if there was any stretch. I do know very quickly that the middle of my graph has been shifted from 0 up to 1, so I must have a vertical shift of 1. Now, the only thing we're missing is our k value, so let's go back and consider that. Okay, well, the first thing that I think we need to address is we can view this two different ways. I'm hoping best picture scenario is that we relate the period of a normal sine curve to the period of the graph we've been given. And since my normal sine curve has a period of 360 degrees and this sine curve has a period of 360 degrees, we should know that there has been no horizontal stretch. The period didn't change. And so therefore your k value would be 1. Now, since it's 1, you wouldn't write a 1 in there. You would simply just write sine x, and we're good. Now, the second part that can help us, and this is what we referenced a little bit ago, your best friend when dealing with these functions. Remember the relationship that your period is 360 divided by your k value. And so if I was to then just blindly sub in, then we should see that 360 divided by 1 gives me 360, and I can solve for a k value of 1. So there is us coming up with the equation if we were given a sine graph. So let me just get rid of that green arrow at the very beginning. And now let's address the second case. Now we have to build in a cosine equation. Well, the nice thing is, if we were to build a cosine equation, then that doesn't change the amplitude. It doesn't change the period. And it doesn't change the middle of my graph. So what's different about the cos curve? It's my starting point. Right now, if I were to take the blue equation on the screen, I know my cos curve starts at the top and falls. This would be the beginning of my blue equation. That's the way it would look. My problem is that's not the horizontal location of that curve. So what I would need to do is take that blue and shift it to the right to then get it to lie on the given graph. So how far do I have to shift it? Well, I need to shift it to the other max. And so I would need to shift that to the right 90 degrees. And there is my equation. Now, quite often the way people will think of that is they're going to know where the beginning of your cos curve always is. That is, it starts at the top and falls. And so where is my first opportunity on my cos graph that I can see where I am at the top and falling? It is at my max. And so I need to shift it to the right to that first max position. Okay, there is us going through and building the equations to our trig curve. Now, this becomes the big complex part. Because this function is periodic and it repeats over and over and over again, there are infinitely many equations that you could have come up with. I think what you see on the screen would be your most common two. However, you could come up with any equation that makes sure that it lies on that given curve. So let me take a couple other situations and maybe we can deal with it. First off, let's examine our cos equation because I think probably the next easiest equation for us to come up with might be using a negative cos graph. So what I mean by that is I'm going to make my cos negative. Now, what does making that cos curve negative do? Well, it takes my cos graph that normally starts at the top and falls and reflects it across the x-axis. So my new curve then would be down here somewhere and rising. Well, if that was the case, then I'm now starting from the minimum of my graph. And as I scan to the right, where's the first time that I hit my minimum? At 270 degrees. That means that I could shift my graph ahead 270 degrees, so to the right 270, if I had a negative cos curve. That new equation that we just created would be another equation that would represent the equation on the graph. Okay, well then that begs that I could use a negative sine curve. And so if I was to begin that process with my sine curve, then what I can do is I could say, well, my sine curve then could be reflected in the x-axis as well. So my sine curve normally starts in the middle and rises. Well, now when I reflect that, it's going to start in the middle and fall. So where's the first instance that I see where my curve is in the middle and falling? It would be 180 degrees to the right. So I can shift it 180 degrees to the right and create yet another equation that would represent the given curve. Now, I also threw out, again, there are infinitely many equations, because we haven't even thought about shifting that curve to the next maximum that would occur over here, to the next minimum that would occur all the way over here, let alone all the maximums and minimums that occur to the left. There are infinitely many equations that we could build. Now, don't ask me why, and it's a weird thing that I have in my mind, but when I shift my curve to introduce my phase shift, when I shift it horizontally, I actually think about it as if it was like physical work. And so quite often to me, I want to shift it as little as possible. So, if I were to build this, or see a problem that asked me this, and said build the equation to that curve, and it didn't define that I had to do a sine and a cosine, I only had to come up with one, that would be my number one choice. Because it doesn't require a phase shift, it's less transformations for me to consider, less work. If I was to come up with a second equation, then I would come up with my cos graph, that first blue one, because I view shifting to the right 90 as less work than shifting to the right 270. It never matters which equation you use, as long as we make sure that it represents the given curve. So let's jump in and play with a few more curves. Okay, we're going to go a little faster on this one. So what I would recommend doing is let's pause the video in a moment, and I want you to go through and search that when given the equation, y equals a sine or cos, doesn't matter, that we know that if we could go through and find a value for a, k, c, and d, then we can build the equation. What I'd like you to do is pause the video and go on the hunt for those four values. Try it now. Okay, we're back. So if I was just to kind of work left to right a little bit, then the first thing I might come up with is my a value. I notice that my total height is 2 units. I go from -2 down to -4. That means that I'm going to have an amplitude of 1. If we then focus in on that amplitude of 1, then I know that I'm going down 1 to get to my middle, or up 1 to get to my middle. So I know that I have a d value of -3 as the middle of my graph. Now, to come up with my k value, well, my k value is then going to be, and maybe we can look at it, as we go, well, I was given one bottom, a minimum, and I was given another minimum. So the distance between those minimums is 180 degrees. That is my period. And if my period is 180 degrees, then it's half of what it used to be, what a normal trig curve is. And so therefore, for me to get half the period, I need to have a horizontal stretch by a factor of 1/2. My k value would have to be 2. Again, though, I'm going to have a lot of people that are going to use that relationship and say that my period is 180, multiply out your k, divide out your 180, and algebraically solve for k. There's our 3, and we are good. Okay. Now, given those properties, what I'd like you to do, pause the video and try to build one sine equation and one cos equation to match up. Go ahead and pause it now. Okay, we're back. So, as I'm working my way through this now, okay, I should be good that if I was to see where is the beginning of my curve, well, the beginning of my curve starts at a bottom. None of my trig curves start at a bottom. I have a cos curve that starts at the top and falls, and I have a sine curve that starts in the middle and rises. Well, the easiest way for me to get down to a bottom and rising would be to take my cos curve and reflect it. So I'm going to use a negative cos graph to be able to go through and build the equation. Okay, I'm going to use a negative cos graph that needs an amplitude of 1. I would plug that in. Of course, you would never write in the 1. That's bad form. We would simply state negative cos. I have a k value of 2, and I require no phase shift because my graph is now matching its starting value. I need to adjust it so that the curve has a middle vertically of -3, and there's my easiest equation to build. I'm hoping that we all had that same cos graph. Okay, now I need to come up with a sine curve though. If I was to build my sine graph, that wouldn't change my amplitude, so I know that I'm going to have a sine value that has a coefficient of 1. It doesn't change my period, but it will require a phase shift. So for me to get to that, then this sine curve right now, if I was to start to sketch it, would start in the middle and rise. So where is the first opportunity that this given curve is in the middle and rising? It's right there. So if I can figure out what are the coordinates of this point, then I can figure out where my starting value is, and therefore what my shift would be. So for me to come up with the coordinates of that point, I notice that I'm halfway between that bottom and that top. Well, that means that I need to be halfway between 0 and 90. Well, that gives me a little confirmation then that my x value must be 45. Now, it doesn't even matter if you come up with the y coordinate. But what I know now is that I have to shift that graph to the right 45 degrees. Now, I do get a little confirmation on my picture that that's at 45 because I can then trace up onto my x-axis and notice that I have 4 grid lines that take me up to 60, so each grid line must be 15, and therefore I arrive at a value of 45. My guess would be that those should be the 2 first equations that you would have gone through and built. Now, we know that we have infinitely many answers. Let's take a peek and see what we could have also come up with. I would have expected several people to come up with a different cos curve. I would have loved the negative cos graph because then it requires no phase shift. However, if we started with a positive cos graph, then my normal cos curve starts at the top and falls. I would have to shift it to my first maximum. That would require a shift right 90 degrees. That green equation, totally good. Also though, maybe we went through and dealt with a negative sine curve. Well, if I took a look and I noticed that my sine curve starts in the middle and then rises, then to start in the middle and fall would be my negative sine curve. There's that first opportunity. Well, how far is it then from the very beginning, my y-intercept, all the way across to that blue point? Well, I'd have to travel 90, or I'd have to be exactly between 90 and 180. That means that I would have to move 45 degrees from 90 or 45 degrees back from 180. That's going to put me at a value of 135. And any of those equations then would represent the equation of the given curve. Okay, let's try another one. So what I'd like you to do is just take a look at this given graph. And I want you to notice a couple things. Okay, first off, the big highlight when you take a look is that we have a pretty ugly y-intercept. It shouldn't bother anybody. So don't let that ugly y-intercept get in your way. We'll see why it really doesn't matter as we go. The second thing I would like to address, though, is what if the maximum and the minimum values were not given? Well, then what you would really want to do is be able to read out those values. So take a look at the pictures that are given, and the first thing I would always do, label your maximum and minimum values. Okay, we're going to take a look at the picture, and we love the fact that the maximums and minimums were given. We're going to list out some properties. So the first thing we notice is that we have an amplitude. The curve runs a height of 1 unit, and therefore my amplitude would be 0.5 or a half. Never matters how you write it. Okay, now I take a look at my period. Well, my minimum occurs here at 30, and my maximum occurs at 210. So the distance from my minimum to my maximum is 180 degrees. And I know that that is always half the period. So if I were to double that to get back to its minimum, I know that my period then is going to be 360 degrees. So I know that I have a k value of 1. Okay, where is the middle of my graph? Well, if I go up a half from the bottom or I go down a half from the top, then I'm going to get to a y value of 2. And so my d value is 2. We're also getting much better at this. We know then that whether I have a c value or what my c value is will depend on whether I choose a sine or a cos curve. So let's start it off with what I think would be the easiest equations to build. But I do want to give you an opportunity to go through and try to build the equations on your own. So if you're feeling super comfortable, pause the video. We'll see if we match up. Okay, we're back. So a couple of the things that I hope that we would do. My guess should be that I think we should use a negative cos curve as our best option. Again, in my mind, phase shift, a horizontal shift, is physical work, and I want to do as little as possible. So if I go to a negative cos graph, then I am starting my curve at its minimum, which means I only have to shift it to the right 30 degrees to get to the first minimum I can see. Put in the middle of the graph, and there's our first equation. Now again, I have to come up with a cos and a sine curve. So now I need to come up with a sine graph. Well, I know that my sine curve starts in the middle. So I'm looking for the first opportunity where I'm in the middle. Well, that looks like my middle because it has a y value of 2. So what are the coordinates of that point? And really all I care about is what is the x coordinate. Well, I know that I have to be halfway between 30 and 210. So the distance between those two values is 180, which means if I go 90 degrees in from one side or 90 degrees back, I'm going to arrive at the middle. And that's going to get me to a value of 120 degrees. So for me to then be able to go through and build my sine curve, as I clean up that graph a little bit, knowing the coordinates of that 120 are going to tell me that then I could build my 0.5 sine. I shift it to the right 120 degrees to get to my starting point. So some other equations that we could have dealt with. I don't think that there would have been anything wrong at all with using a positive cos graph. Remember, it's kind of my thing that I view a phase shift as physical work. I would have had a bunch of people that would have said my normal sine curve starts at the top and falls. So the first opportunity where I see that graph at the top and falling is at my maximum, I will just shift it there. I think that that should give us our most common responses to that, but again, we've talked, there are infinitely many graphs. Okay, let's try one more and see how we're doing. So what I would like everyone to do then is just pause the video and let's go start to finish on this one. And again, we'll see if we match up in the end. So pause it now. Okay, and we should be back. So a couple things we should notice, that we go all the way from a value of -1 all the way down to a value of -7. That means that our curve has a height of 6 and therefore an amplitude of 3. We also notice that I haven't been given maxes and mins enough to just blindly go, well, I can see the coordinates of that. And if I were to scan up to try to be able to see, I'm estimating up there. Okay, I never want to estimate if I can avoid it. And I actually have enough information on this graph to be able to work my way through. I have that my minimum goes from 35 up to a maximum of 125. So horizontally then, the distance from minimum to maximum, half the period, is 90. Well, if half my period is 90, then my period is 180. And that period is half my normal period, which means I need a horizontal stretch by a factor of a half. I need a k value of 2. Okay, the only big thing for us to then figure out is let's work our way to the middle. So if I was to go up 3 units from the bottom or go down 3 units from the top, then I'm going to arrive at my middle of -4. With those properties, then we can start to build our equation. For me to go through, I think I would come back to, and let's just deal with it this way. Let's deal with a coast curve first. So to build my coast graph, maybe I deal with my negative coast graph, because again, I view it as physical work. So I would want to deal with a negative coast curve, because then that would allow me to only have to do a phase shift of 35 degrees to the right. That would be my first equation. However, I can see a bunch of people saying, why bother reflecting it? I'll just use a positive coast graph, but it does mean that I have to phase shift it all the way over to 125. Ugh. Sorry, I can't help myself. Those two would be the most common coast graphs that I would expect to see. Okay, now we got to deal with a sine curve. Well, my sine curve is me looking for my first opportunity to be in the middle and rise. Well, I know that I have to be half the distance that the max and the mins are apart. So since they are 90 degrees apart, if I go 45 degrees from one side or the other, then I will arrive at the middle. That's going to give me an x value of 80 degrees. And so if I was to build that, then I know I could use a positive sine curve that is phase shifted 80 degrees to the right. Or, and this would be one that maybe you wouldn't expect so much. Again, it's in my head, but if I was to go through and clean up that video, or sorry, that screen, that graph, and then focus in on, well, this would be the first opportunity that I was in my middle and falling. I would actually have this point over here that would be in the middle and falling, and that would be a shorter phase shift. It would require me to phase shift it, on a negative sine curve, to the left, which tells me I would have to be adding that value on the inside. Now, how far do I have to phase shift it to the left? Well, it would have to be half that distance from my max to my min, or a quarter of my period. I'm going to have to phase shift it to the left 45 degrees. Now, that's my error. 45 degrees from the 35 degrees. And therefore, it would be a phase shift left 10 degrees. Those would be your 4 most common graphs that I would expect to see. Hopefully we've got some practice and we're good at coming up with the equations of those. This becomes the first step in us when we get to solving application problems dealing with trig functions. Okay, let's jump in, get a little bit of practice. Best of luck.